called limits that led us to differentiation or derivatives, slope of the tangent, slope of instantaneous velocity. And now we're going to, in chapter 3, we learned how to use or apply differentiation rules. And now we're going to use differentiation and deeper into applications, basically. So here's the first application that we're going to look at. It's in 4.1, max-min. Finding max-min of functions. The first thing we have to look at is just, let's look at the graph. It's not our best friend, it's just a regular graph of a function, let's say this. And then I would like to look at another function, let's say this. Obviously, this is a local max. And this is a local min. Local, in some books, you're going to find it as relative max instead of local max. They mean the same thing. Or relative min instead of a local min. What do we mean by local min? Well, I'm able to show an open interval around that point where the function exists. So the function must exist on both sides for a local min to exist. And these function values have to be smaller than it for this one to be a local max. This one is a local min because the function exists on both sides and all function values are larger than this one. It's a local min. Let's look at the other situation. Here, this cannot be a local min because I cannot show the open interval around it. The function does not exist on this side. The same thing here. Endpoints cannot be local. Endpoints cannot be local max-min. Ever. But what they can be, like in this situation, this one will be called global. Also called in other books absolute. Max, because it's the highest value of this function. There's no higher value than this. Also, this will be not a local because it's at the endpoint of the interval, but this is an absolute min. This function also has a local min and a local max. Local max, local min. Can the local min or local max be also absolute? Yes, it can. So let's look at a graph and identify. I like these 4 graphs here in the book. Up to you what you would like to choose. We want to look at 5. Perfect. So let's look at this point, which is the first one. Can you all see? Yes? Can you see number 5? Okay. So this point here is at the end point of the interval. It cannot be local, and it's not the smallest. So this one is nothing. This up here does not exist. When I say the function has a maximum, I have to give you the maximum is 15. If I say, in this case, I'm going to say the maximum is 3.9. And somebody else says, no, it's 3.99. And the next person says, no, it's 3.999999. And we will argue forever because there is no max. The point does not exist. It's an open point. So there is no max, no local max, no global max, nothing. What about this one? This one is a local min because I can show the open interval left and right. And I can tell you it's at 2 and the minimum is 2. This one, yes. It's not only the local max, but also relative max, absolute max, right? Local or absolute, local or relative is the same. So it's the relative and the absolute. Why? It's relative because I can show the open interval, and it's also absolute because there is no other value higher than it, and this is 1, 2, 3, 4, 5, I think, right? This one, is this a local min? Yes, it is. Not an absolute, of course, because there are others smaller. So, and I can show the open interval around this point, and I'm able to read it for you. It's 3. This one, it's at the end of the interval, so it cannot be absolute. It cannot be relative, and it's not the largest, so it's nothing. This one doesn't even exist, and we cannot even talk about it. This one doesn't even exist, and we shouldn't even talk about it. So this function has a local min, a local min, a local and absolute max.
Would we label the global max, or like those endpoints that don't have anything around it?
You don't have to write anything, depending on the question. But if it says just find the local max, local min, absolute max, absolute min, you will not mention those. Yes, no?
Do we write the whole point or just why?
Well, it depends on the question. Very good question. Excellent. If it says, excellent question. Thank you. If it says, where does the function have local max, local min? I would say at x equals 2, at x equals 3, at x equals 4. If I'm asked how much, then I would say the maximum is, the minimum is. So if I'm asked where, I give x. If I'm asked how much, I'm giving y. Because it means that I'm asked about the function value. So where is x? So for example here, if I ask you where is the local minimum, you would say at x equals 2. If I ask you how much is the minimum, you will say the minimum is 1. Very good question, thank you. Is that clear? Okay, so where means location. How much means the y value, or the function value there. Great job. Okay.
Will we ever say like the whole point though?
It could. It could. Identify, here's the question. Very good question. So identify the points of max min. Then I would say 2, 2 is a local min and an absolute min. This is my next step anyway.
Okay.
But I want to answer your question. So if I'm asked the point, then I'll give 2, 2 is local min. Or 2, -3 is the local max. So I give the point, yes. I have to keep my pages numbered because many years ago when I started doing this one time, I dropped them. And they had no number. So I had to, it took me like 5 minutes to put them back together. Okay, next topic here, very important, critical numbers of a function, of course. Critical numbers or critical number of a function. Okay, first of all, what is it? Critical numbers come from 2 possible sources. When f prime of x is undefined, very crucial now, but f of x is defined. Critical numbers, of course, are x values, right? Obtained from f prime being undefined where the function is defined. And the second possible source is from f prime of x being 0. So something important happens at those points, potentially. That's why they're called critical numbers. So a function doesn't have to have critical numbers at all. A function may have critical numbers coming from one or the other. Or a function can have critical numbers coming from both. Undefined situation and when the derivative is 0. Why are we interested in critical numbers? Is that if a function does not have critical numbers, it will not have max min. If a function has critical numbers, is it guaranteed to have max min? No. But it's certain that if it does not have critical numbers, it will not have max min. Which of those critical numbers create max min? We'll have to see. You'll have to wait for a couple of minutes and you'll see which ones. Okay.
I'm sorry.
Yes.
Like a local maximum.
Exactly, or absolute.
Oh, absolutely.
Of course, yes, exactly. So I would like to start with a problem on page 281. Let's start with a simple one, which is 30, page 281. And we have f of x equals x to the third plus 6x squared minus 15x. In this problem, we are asked to find the critical numbers. I'm going to add more to this question, not just the critical numbers. I'm going to show you what we're looking for. Okay, this is a function. What type of function is it?
Polynomial.
Polynomial, cubic, very good, awesome. Do you think that its derivative, when we determine the derivative, could it be undefined? No, because it would be a quadratic function. So let's find the derivative. So the f prime of x is 3x squared plus 12x minus 15. And now the question is, does this function have critical numbers? So I have to check both sources, but f prime is always defined. Always. So this particular function may have critical numbers coming from f prime being 0, but definitely not from f prime being undefined. Would you agree? It's quadratic, so it's defined all the time. So then I have to try to solve this equation now, which is 3x squared plus 12x minus 15 equals 0. Always remember to clean up everything, simplify as much as possible, factors, and do whatever it takes. Yes, please.
That's, I had a question. I don't think we'll have to deal with it, but so when we take the derivative, it's still a polynomial.
Yes.
But if we kept on taking the derivative, would it not
At
have
some point in
critical
time, we would have 0.
numbers? Okay.
Correct. Yes. Because the next one would be 6x plus 12, and the last one would be just 6.
Okay.
Correct. Very good. So we will divide both sides by 3, and we get x squared plus 4x minus 5 equals 0. And I'm hoping that we can quickly factor this and get the two solutions. Since it's quadratic, we have x plus 5 and x minus 1. And we have two options as -5 and 1. Would you agree?
Mm-hmm.
Now, remember we used the table to graph piecewise defined functions and etc. other things. We're going to build on the same with the first derivative first and the function second. Create your own chart if you don't like this, but I will always use the first derivative and then the function, and then later on I'm going to add one more row to it. Okay, so then I have -5 and I have 1, and obviously 0 and 0. I would like to analyze or determine the sign like we just did a few minutes ago with the acceleration and the velocity. A few minutes ago we did that. So here is the derivative, and I would like to determine the sign of the derivative to the left of -5, between -5 and 1, and outside to the right-hand side of 1. But it's not a problem here because I don't need to plug in numbers. I know how that looks like. It's a quadratic function opening upward. So in between solutions, the sign would be right, and outside would be positive. Or you can plug in numbers. That's fine too. So positive, negative, positive. You can plug in numbers if you wish. Okay, now we'd like to discuss one more thing before we continue and draw conclusions here. We know x cubed, don't we? Does x cubed have any max min?
Yes.
Yeah.
But doesn't it like, when it crosses the origin, doesn't it like, it's a triple? No?
One more time. X cubed. No turns. Remember, I'm going north on I-5 and you say come back. Then I turn. By turn, we mean maximum, right? So here's x cubed. Correct? Correct? No max, no turn, no min. Okay, perfect. So now, what can you say about this function, about the slope of a function at any point? What type of slope does it have?
It's greater than 0.
Excellent, because the function is always exactly. So we will conclude immediately this is the first derivative test. If the first derivative is positive, what do we conclude about the function? What does it do? Very good. When the first derivative is less than 0, what does the function do? Yes. So please keep that in mind. The function will always increase if its derivative is positive, and it will always decrease if its derivative is connected. If it's decreasing, the derivative is negative. If the derivative is negative, it's decreasing. Perfect. Okay. So now, we determined that this function, we determined its critical numbers, and we found 2 critical numbers. Here's what I see. I see the first derivative being positive, then being 0, and then being negative. What type of point is this? Positive, 0, and negative. Maximum. What about this one? It's negative, then it's 0, and then it's positive. What type of point is that? Yes. So we will have to determine, because I can't tell you what they are, so I have to determine these points in the y values. In the function f of x, I will plug in -5 and 1 right this moment. So in y equals, we had x cubed, and we had plus 6x squared, and minus 15x. And I want to plug in only -5 and 1. That's all I care about. At -5 is 100. And at 1, it says it's -8. About this function, that is x cubed plus 6x squared minus 12x, can you please tell me what happens? What is the limit when x approaches -infinity? These are too small to mention. When x approaches -infinity, where does this go? Of course. And when x approaches infinity, where does this go? Of course. Good. At this point, I'm ready to check that these 2 rows work well together or not. That's how I catch my mistakes. Ready? So from -infinity to 100, what does this function do? Decreases, correct? Increases, correct? From -infinity to 100. Is that supported by the correct sign of the derivative? Yes, it is. Great job. Between 100 and -8, what does this function do? Perfect. Is that supported by the correct sign of the derivative? And what about between -8 and infinity? Is that supported by the correct sign of the derivative? So all our calculations are correct. I'm not going to graph the function. We will very soon. But here's what it says. From -infinity up to 100, down to -8, and up to 100. Obviously, this is not the graph. I'm just putting the y values in there. So this is definitely this situation. And there is no question that -5, 100 is what type of point, and 1, -8 is what type of point? Local max, and local min. And now we're going to put everything together with just a summary. So, yes, please, Noah.
So is so -5 and 1 are critical points.
Where the max min happen. The critical numbers, not the critical points. -5 and 1 are critical numbers. Critical numbers change into max min only if the derivative changes sign. If the derivative never changes sign, even if the function has a critical number, that critical number is not a max or a min. So if you remember, I gave you that simple example with x cubed, and the derivative is 3x squared, and this is always positive. Although the critical number is 0, when you set f prime equal to 0, 3x squared equal to 0, you get x equals 0. But this function is always positive. So on the right hand 0 and on the left hand 0, on the right of 0 and the left hand 0 for you, the function, the derivative is positive. It does not change sign here, which means it cannot be a max or a min. If the derivative at a critical number does not change sign, either from positive to negative or from negative to positive, the critical number, it does not turn into a max min or min. Any questions? Any questions?
Yeah, I have one.
Yes, please.
Could you just refresh about, or just for a second, how it was -5, then we get positive for,
This was plus. So the factor form is x plus 5x minus 1 equals 0.
okay, okay, gotcha.
Is that okay?
Yep.
Very good. In summary, okay, so this is a summary of what can happen. We can have a critical number where the derivative is 0, or undefined, for different situations. And it changes sign from positive to negative. It changes sign from negative to positive. Or it's always positive, or it's always negative. Positive, negative, negative, positive, always negative. This results into a local max. This results into local min. Awesome. Oh, you know what I meant. So what does this mean? Nothing. Although it has a critical number there, because the derivative does not change sign, does not turn into a max min. What about this one? Nothing. What about this one? It can be undefined, where the function is defined. And this will be a local max. The same thing as before, local min, and this, nothing. Questions? Okay, I would like you to choose another. Let's look at one more.
Because
Yes?
because the x was -5 and f of x was 100,
Yes.
it turned from a negative to a positive.
Yes, because we plugged it in the function.
Right, so that's why it's the max, because it's this.
Not because of that, mainly because it's positive, 0, negative. Positive,
Right, positive.
0, negative.
Okay. Oh, okay. Yeah, makes the triangle. Okay.
So I would like us to look at one more problem and then look at how to study a function on a closed interval. But before that, I'd like to choose one more. And we're going to do more than just critical numbers. I don't want to wait. So we're going to use any function you want from here. And not just answer about critical numbers, if it has critical numbers or not, but also study them beyond that and see if they turn into max-min. I would like to look at a rational function as well. It's up to you. Whatever you would like to see, or something with these weird exponents. We only looked at the polynomial function from problem 30.
What's the weirdest one on there? Unless
I'm not really sure.
it's even 36.
So the other class last night they chose 44. It's up to you.
35.
Surprise me.
36.
36. Okay, perfect. So let's look at 36. On page 281, 36. Age of p equals p minus 1 over p squared plus 4. Very good. We are asked to determine the critical numbers, but we're going to take it one step forward. And we're going to look at find critical numbers, but also study the critical numbers and see what they represent and how and so on and so forth. Okay, so first of all, I have to find h prime of p. Top prime is 1, p squared plus 4 minus p minus 1 times the denominator prime, which is 2p. And then the denominator is p squared plus 4, everything squared. So it was a rational function. We differentiated the top. We got 1 times the denominator minus the numerator times the denominator prime. Of course, I'm going to try and simplify as much as possible. And that's why, if you remember from that blue form, we looked at one problem in which I said that needs to be completely simplified for this. That's why we need to completely simplify it. So I will distribute. So h prime of p squared plus 4 minus 2p squared and plus 2p over p squared plus 4 squared. So this is negative p squared plus 2p and plus 4. P squared plus 4, everything squared. And yes, like I mentioned before, please do this. It's not the best situation or the nicest situation, only because when I set this equal to 0, the numerator is not factorable. So I will have some radicals in there or some approximations. But now I'm ready to discuss critical numbers. They can come from h prime of p undefined at a value of p where the function is defined. But both functions are undefined when p squared plus 4 is 0. But p squared plus 4 is never 0. So they would have been the same, undefined both, but they're not defined. They're defined everywhere. So that's not a case. That's not possible. The other possibility is when h prime of p is 0, which means p squared minus 2p minus 4 is 0. Now I have no choice but use the quadratic formula on this. So then I have p equals negative b plus or minus b squared minus 4ac over 2a. Or 2 plus or minus is the square root of 20, so 2 to the square root of 5 over 2. Or 1 plus or minus the square root of 5. Notice that I did not simplify the sum. I factored 2 and simplified or separated into 2 fractions. So it's 1 plus or minus the square root of 5. So these are the 2 critical numbers. And in the table, so this is h prime of p, and this is h of p.
So why didn't we solve for b at the bottom of it?
A fraction is 0 only when the numerator is 0.
Okay.
So, and this fraction will be undefined when the denominator is 0. But the denominator is p squared plus 4, it will never be 0. So the only critical numbers for this function can come only from p prime being 0, which means only when the numerator is 0. Correct, everyone? Okay, perfect. So 1 minus the square root of 5 is a negative number, and 1 plus the square root of 5 is a positive number. So I want to study the sign. Yes, it's nice. I know it has two critical numbers, but I'd like to know whether they eventually turn into max min. So go back to the derivative, and I realize that this is always positive, and this is a linear function with a negative leading coefficient. Quadratic function with a negative leading coefficient, and looks like this, and it crosses at negative 1 minus the square root of 5 and 1 plus the square root of 5. And it looks like this. And in between solutions must be about the x-axis because it has a maximum. So away it's negative, and in between is positive. Or you just plug in numbers. I'd rather not plug in numbers if I can avoid it. So this is positive and this is negative. So whatever this is, and we can plug it in, and whatever this is, we can plug it in. We know that the derivative changes sign at this point, and it changes sign at this point. Both these turn into points of extrema. Extrema, extrema. So what will this point be? 1 minus the square root of 5, comma, the y value of that. What type of point would that be? A minimum, right? Because it's negative, 0, and positive. That's a situation for negative, for minimum. Negative slope, 0 slope, positive slope. What about the other point? 1 plus the square root of 5, comma, this.
Excellent.
Yes, because on this side is positive, then it's 0, and then it's negative. Good. Any questions? Would you like us to find these numbers, or is that the idea clear? We want to find them? The y values? Let's do it.
Sure.
So the function was, so please be careful. It's a very good exercise. Make sure that you put parentheses around the numerator and parentheses around the denominator for any rational function. So it was p minus 1 at the top, p minus 1, close the parenthesis and divide by p squared plus 4. And then we go to second table, and we have 1 minus the square root of 5, and enter, and then 1 plus the square root of 5, and enter. So the values are negative 0.4 and 0.15. Now to be exact, once I approximate, I'm not really giving you the exact max min. I should just plug in 1 minus the square root of 5 and give you the exact without approximation. But for now, that's fine. I'm going to say that negative 1 minus the square root of 5, comma, negative 0.4 is a local min, and 1 plus the square root of 5, comma, 0.15 is a local max. We established that basically using the first derivative test, saying that when the derivative is negative, the function is decreasing. When it's positive, the function is increasing. Questions? Okay, so let's look at one more topic. A function on a closed interval. The two functions we looked at before did not have the domain restricted to a closed interval. The next one will. So in these problems, we are asked to study the function on a particular closed interval and identify the absolute max, absolute min. I will say comma, also the relative max, relative min. So we did look at the rational function. You may want a radical. You may want a natural log. You may want an exponential. 59, 60, 55, it's up to you. Which function would you like to look at?
55.
55. Very good. So 55 on 281. And we have f of t equals t times the square root of 4 minus t squared. The closed interval is given to us. That's carved in stone, and we can change that. So we can start our table. F prime is first, and f of x is next. Carved in stone means this. We cannot look beyond what we are given. So here we are asked basically to determine absolute max, absolute min, but I'm going to add relative max, relative min, and critical numbers, of course, and etc. So we're going to determine what first?
Side or zeros.
The derivative. We only want to find the critical numbers. We're not going to graph, but you're right. Once we get to graphing, the x and y intercepts will be key points. Absolutely. Yes. Here we're not graphing. We're just studying the sign, saying it has critical numbers, it has absolute max min, and here they are.
Okay.
So f prime of t, this is a product, t times the square root. So we differentiate the product, we obtain a sum. Be very careful, this is a very important type of problem because we would have to completely simplify this and turn it into a ratio so we can solve. If we don't turn it into a ratio, we will not be able to solve the equation. So the first function prime is 1. The second one is 4 minus the square root of the 4 minus t squared plus t, and now careful, it's 1 over 2 the square root of 4 minus t squared multiplied by negative 2t. Let's simplify that piece before we find the least common denominator. So the square root of 4 minus t squared, the 2's go away, but there is a minus t times t, so it's negative t squared over the square root of 4 minus t squared. And now I have no choice but to find the least common denominator and take it from there. So I simplified the negative 2, or the 2 with the 2. I have a negative t times a t, so that's negative t squared. And the least common denominator is, of course, there is nothing else. The square root of 4 minus t squared, but this one needs to be multiplied by the square root of 4 minus t squared. So what do we get next? Yes, 4 minus t squared, which is not a friendly expression. So 4 minus 2t squared is not friendly at all. Yes, arrange it in descending order and factor out the 2. Again, I'm in the same situation as before. I can't factor t squared minus 2. I mean, it's not factorable. The solutions are plus or minus the square root of 2, but they're not nice numbers, right? Irrational numbers. So we have to put it in descending order. We have to factor out the greatest common factor and the negative leading coefficient. We don't want a negative leading coefficient in the expression. So then, 2 questions here. F prime of t, undefined. F prime of t, 0. Remember, we are after critical numbers. Critical numbers can come from 2 sources. When the derivative is 0, but the function is defined at that value, when the derivative is undefined, but the function is defined at that value, or when f prime of t is 0. Let's start with the second one. When is this expression 0? Only when t squared minus 2 is 0 or t squared equals 2, take the square root plus or minus the square root of 2. I immediately go to my table. The square root of 2 is 1.4, but the negative square root of 2 is out here. So only t equals the square root of 2. Okay. Does this function, is this function undefined? So we have done with the second option. But is this function undefined? Anywhere between -1 and 2. Don't say anything. Look at the original function first. The original function has, we haven't determined the domain, but they are giving us, we are restricted to this anyway. But in any event, this was not in the denominator. But now it is. Where is this 0? When 4 minus t squared is 0. And there are two options for 4 minus t squared to be 0.
Plus or minus 2.
Correct. Excellent. Thank you. So 4 minus t squared is 0 when t is 2 and when t is -2. Uh-oh. Here it is. That is a critical number. The function is defined at 2, but the derivative is not. Perfect. So then we have 0 here. We have to study the sign of the derivative. So here's our derivative. I refuse to plug in anything in here. Why? Why do I refuse to plug in numbers into over the square root of 4 minus t squared? Because the answer will always be, I don't care for it. So I'm going to plug in numbers only into -t squared plus 2 to find the sign. And again, I know the answer because that is a negative, it's a quadratic function with a negative leading coefficient. It crosses at negative the square root of 2 and crosses at the square root of 2. So between negative the square root of 2 and the square root of 2, it must be about the x-axis. So this must be the case. And now you can plug in 1.9 if you want, but there is no need. This is below the x-axis. When I study a function on a closed interval, I must determine these three values. And then make a decision. So in the graphing calculator, I will put t to the square root of 4 minus t squared. And I'll plug in 0, the square root of 2, and 2. So in y equals, we have t the square root of 4 minus, I don't need to do this, we can do it by hand, but let me change that into 4, I don't know why I put x. Perfect. So I'll plug in -1, I'll plug in the square root of 2, and I will plug in 2. So the answers are -1.7, 2, and 0. Moment of truth. I need to make sure that these two rows work well together. If they don't, I have an error. I have to start maybe from scratch. From -1.7 to 2, what does the function do?
Increase.
Is that supported by the sign of the first derivative?
Yes.
Excellent. From 2 to 0, what does the function do? Is that supported by the sign of the first derivative? Again, I'm not graphing the function. I'm just plotting an idea of the y values. Just an idea. -1.7 up to 2, down to 0. So what do you say about -1, comma, -1.7?
It's the local.
It cannot be local at the end of point of the interval, right? Because the function does not exist on this side.
Oh, okay.
So it's the absolute minimum. So -1, comma, -1.7 is the absolute min. Global min, absolute min. What is the square root of 2, comma, 2? Local max and also
Absolutely.
absolute, there is nothing higher. What about this point? 2, comma, 0.
Nothing.
Very good. Nothing. It's not absolute. It cannot be local. Cannot be absolute max, absolute min. It cannot be local because it's at the endpoint of the interval. The square root of 2, comma, 2 is the absolute and local max. And -1, comma, -1.7 is only the absolute min. Since it's at the endpoint of the interval, it cannot be local. This is the way we study a function on a closed interval. Any questions?
So -1.7 is the min, absolute min, and 2 is the absolute
Max.
max.
Yes. And I listed the full points. But you can say that the maximum value that this function has on the given interval is 2. And the minimum value that this function has on this interval is approximately -1.7. Because I think it was not exact. Any questions? Any questions? So that's a situation. I wanted to look at a word problem. We have 5 minutes. Maybe we just start it. Let's just start the problem. Let's just read it, and or at least just talk about it, and we can do it after the test a week from today. So here is 69. Because we want to see where this is applicable. So at least let's discuss the problem. Okay, so between 0 and 30 degrees, that's a closed interval. 0 and 30 degrees. The volume being cubic centimeters of 1 kilogram of water and the temperature uppercase T is given approximately by this formula. Find the temperature at which water has its maximum density, which is the derivative. So we will have to differentiate this function. It's a cubic function. It will not have critical numbers coming from f prime being undefined. We agree. But it will have critical numbers coming from f prime of x or v prime of t equals 0 because it's cubic that changes into quadratic. So we will find two solutions. So this is an application in which we will see what happens between 0 and 30 degrees. And that's a typical example of a function to be studied finding max min on a closed interval. Are we ready for this test? Next